Question number 1, rolling boulders at the Romans. Defenders roll boulders down the slope toward the Romans. The Romans are sheltering behind a wooden fence while they are laying siege to the town. Question number 1, the first boulder rolls 31 metres. So the first thing we think of is that as a distance down the slope before it hits the fence. It starts at rest, so VI must equal 0, and accelerates at 4.3 metres per second. Show that the boulder is rolling for 3.8 seconds. And so the first thing we do is we write down all the variables. So we've got d, vi, a, and we're looking for a time. So looking for an equation that doesn't have vf in it. So we look at our formula sheet, which equation doesn't have vf in it. This one here doesn't, so we rewrite it over on our page. D equals VIT plus a half AT squared. We know that VI is 0, so 0 times any time is still going to give me 0. So D equals a half AT squared. You can either use equation solver here. I know I'm looking for time, and so D divided by half A square rooted is going to give me time. Now if I rewrite all this up here, 31 metres divided by a half times 4.3. If we grab out our calculator, so shift square root, open bracket, 31 divided by open bracket again, 0.5 times 4.3, close bracket, and I get an answer of 3.797, which is 3.8 seconds. Now, I would always recommend writing out the answer to more significant figures beforehand so that you can prove that that's the answer you're looking for. A lot of people go back and put 3.8 into the equation. Don't do that. Actually get the answer using all the information they've given. B. The second boulder, which had a mass of 45 kilograms and a speed of 16.5 meters per second, took 0.73 seconds to come to a stop when it smashed into the wooden fence. Calculate the average force exerted by the boulder on the fence during the stopping time. So again, we write down the things that we know. We know M, we know VI, we know that VF is going to be 0, we know the time, and it says calculate the average force. And so we could use impulse, so we could use force equals change in momentum, and change in momentum is impulse divided by change in time. And we could work out that impulse, which is PF minus PI. I know the PF is 0 because it stops. PI is mass times velocity. I know the mass is 45 kilograms. I know that it was initially traveling at 16.5 meters per second. 45 times 16.5 gives me 742.5 kgms minus 1 of momentum. So the change of momentum is 0 take away 742.5, which is minus 742.5. Now the force is going to be that change of momentum, 742.5. The negative just indicates direction, and divided by the time of 0.73 divided by 0.73, which gives me 1,017 newtons, which is worth an E. A different way of solving this is using F equals ma, where acceleration is change in velocity divided by change in time. This way is probably a little bit simpler because the velocity changes by 16.5 in 0.73 seconds. So 16.5. This gives you an acceleration of 22.6. And then we know the mass is 45 kilograms times the acceleration of 22.6 times 45, and we get 1,017 newtons. Either way, it's worth an excellence. In one section of the wooden fence, the posts are driven into soft, mashy ground. When the boulders hit this part of the fence moves several centimeters, so D is larger, before bouncing back again to its original position. In the second section of the fence, the posts are driven into hard ground. So when the boulders hit this part of the fence moves less, so D is smaller. Explain what section of the fence would be more likely to break when hit by the boulders. So if we were to use an impulse idea, force is change in momentum divided by change in time, we could say both boulders had the same initial velocity and the same final velocity, so they had the same change in momentum. The soft marshy ground will have a longer collision time, therefore less force, using this equation here. So that's one way of answering it. Question 2, fire bands. The Romans propel fire bands towards the town. Fire bands are lumps of burning material with a small length of rope attached. The fire band is lit and spun quickly in a horizontal circle before being released towards the town. Complete the diagram below by adding labelled arrows to represent the force. So the force is always centripetal, so Fc, and instantaneous velocity, which is always at 90 degrees. Okay, that there is worth a merit. The number of people that didn't do labelled arrows was crazy. On the diagram above, draw a dotted line showing the direction the fire band would travel if it was released from the position above. So it would travel at a tangent. It would continue in the same direction as the velocity. Explain why it would travel in this direction. So it would travel in that direction because it no longer had any force causing it to go around in a circle. The reason this is going around in a circle is because there's an unbalanced force causing it to change direction. If we remove the unbalanced force, then it will continue to go in a straight line following Newton's laws. Let's see if we can write that up. The fire band will move in a straight line because once the rope has been released, there's no horizontal force acting on the fire band. And so the only thing that keeps it going around in a circle is this unbalanced force of tension. Once we get rid of the tension force, it's just going to keep doing what it's always done, which is travelling in a straight line. So Newton's first law states that when the force is zero, an object will move with constant velocity in a straight line. And so that's why it continues at a tangent to the radii. C. A Roman soldier spun a fire band at a speed of 32 meters per second. So this is our velocity. It had a mass of 1.6 kilograms. It was spun with a circle of a radii of 1.2 meters. Calculate the force needed to keep the fire band moving in a circle. If we look at the formula sheet, we've got velocity, mass, and radii, and so we're going to be using this equation here. And we just simply substitute some numbers in. So 1.6 times 32 squared, and a number of people missed the squared, divided by 1.2. We'll grab out our calculator, we use brackets for the top line, 1.6 times 32 squared divided by 1.2, and you get 1365, and we're measuring newtons. That is worth and achieved. D. Explain how changing the length of the rope would affect the distance the fire band would travel once it's released, assuming the Roman soldier continues to swing the same mass, so M doesn't change, with the same tension. Almost everybody missed this whole idea of the same tension force. So we've got Fc equals mv squared over r. And so by changing the length of the rope, okay, so continue to swing. So how does changing r affect v is basically what we've got. So F is constant, M is constant, v and r can change. And so if I rearrange this to make this Fc times r equals mv squared, and then if I make it a v squared equals, so V squared equals FC over M, which we can't change, times R. And so as R goes up, as the radius of your loop goes up, then velocity increases by a factor, or by a squared relationship. And so if velocity goes up, then the distance it travels will also go up. So where velocity is distance divided by time, the time it's in the air doesn't change because of gravity, but if the velocity increases, then the distance it travels must increase. So let's see if we can write that up. So to travel further, the release velocity would need to be greater, which is what we've said has happened. The force needed to turn the fireband in a circle was given by Fc equals mv squared over r. So as F and m are constant, the ratio of v squared over r must remain constant. Hence, if the radius is made larger, then the velocity must also be increased by a squared relationship. So making the rope longer would make the fireband travel further because it is going faster. That there is worth an excellence. A catapult, or a trebuchet, is a machine that throws objects that are too heavy for a person to throw. It works by turning a lever, so this lever over here, which pulls the bucket arm down as the rope goes around it, using a lever rope. This further twists the rope through the base. Okay, so it twists this, you can essentially think of it as a spring through the base of the bucket arm, adding potential energy, so elastic potential energy to the catapult. When the lever rope is released, the bucket arm swings up into the air because of the potential energy, elastic potential energy stored in the spring, and it fires the arm and the projectile which is in it a large distance. This was a fairly poorly done question, so let's have a look at it. Using a catapult to fling a boulder involves several changes of energy. Describe the energy changes from when the bucket arm is released to when the boulder hits the ground. Okay, so if you haven't talked about the ground, then you haven't got your merit. Okay, so the elastic energy in the twisted rope changes to kinetic energy of the bucket arm and the projectile when it's released. The kinetic energy of the projectile partially changes into gravitational potential energy of the projectile as it goes up into the air. So it's flung, it's going into the air, then it starts to come back down, and it hits the ground. When the projectile hits the ground, the kinetic energy is turned into heat and sound. So 1, 2, 3, 4 for merit. Most people got not achieved or achieved for something that should be a pretty obtainable question. B. A 94 centimeter lever is used to turn the pole and therefore wind the rope around the pole. This rope is attached to the bucket arm. At one stage, the soldier applies a force of 630 newtons to each end of the lever as shown in the diagram. So I suppose the first thing we want to notice is that that distance there is not 94 centimeters. It's going to be 0.94 divided by 2 because it has to be in meters, and so this is 0.47 meters. Just like this distance here is not 18 centimeters, it's going to be 9 centimeters or 0.09 meters. And the guy is applying 630 newtons to this side and 630 newtons to this side, but because they're working in the same direction, it's going to create an anti-clockwise torque, isn't it? So it's a torque in an anti-clockwise direction. So it says calculate the tension force in the string. So first thing I want to do is work out what is the anti-clockwise torque. So torque anti-clockwise is going to be force times distance plus force times distance, because there's two forces and two distances. It just so happens that those two forces and those two distances happen to be the same. So you could do this and go times 2, or you could write 630 times 0.47 out twice. Now if we tuck that into our calculator, 630 times 0.47, and I'm going to go times 2 because I'm lazy, and I get 592.2 Newton meters of anti-clockwise torque, which therefore must equal torque anti-clockwise must equal torque clockwise if it's in equilibrium, which is what we're going to get to in the next question. So 592.2 equals force times distance. Now I know the force, no I don't know the force, I know the distance is 0.09, and so therefore the force is 592.2 divided by 0.09. If we chuck that into our calculator, divided by 0.09, we get a force of 6580 newtons. Worth excellence. The next question should be pretty obtainable. State the principle of equilibrium. Use this to explain how you got your answer to question 3b. Equilibrium is when an object's motion is not changing, so it's either travelling at a constant speed or is stationary. This occurs when the forces are balanced. Okay, if you said equal, that is wrong. The forces have to be equal and opposite. It's also when the torques are balanced, so the sum of the torques is 0 and the sum of the forces is 0. Okay, you needed this to be able to answer the question B, because over here I said torque anti-clockwise equals torque clockwise, and that's how you solved it. So the total forces must add to 0 and the total torques must add to 0, or you can say they're balanced. That there is worth a merit. The first boulder is released from the bucket arm with a speed of 47 meters per second at an angle of 27 degrees to the ground. Show the initial velocity is 21 meters in the vertical direction. So I'm looking for this end of my triangle. So I'm looking for Vy. And so if I was to label my triangle, I've got the hypotenuse and I've got the opposite. And so I've got SOHCAHTOA, I've got the opposite and I've got the hypotenuse. And so I'm going to use this one. So sine theta equals opposite over hypotenuse. I'm looking for the opposite, so it becomes opposite equals h sine theta. The opposite is actually Vy. The hypotenuse is actually V sine theta. So I can simply put in 47 times the sine of 27. You need to make sure your calculator's in degrees, so if you go shift menu, you can see that my calculator is actually in radians, so I need to click it to degrees, exit, and then it's 47 times the sine of 27, which gives you 21.33. 21.33 ms minus 1, which equals 21 ms minus 1. So notice how I have got the unrounded answer there. This is what they're looking for when they're marking really quickly. They're looking for, it's a show question, they're looking that you've actually managed to figure it out. So if you've got 21.33, boom, you're going to be in luck. Okay, E, describe what happens to the boulder's horizontal velocity during its flight. Well, if there's no air resistance, then the horizontal velocity of the boulder remains constant. It doesn't change. So that answer there is worth an achieved. F, calculate the maximum gain and height the boulder obtains. Well, in the previous question, I know that VIY is 21 meters per second. I know that VF, the speed at the top, is going to be 0 because he stops. I know acceleration is going to be minus 9.8 meters per second because it's in the opposite direction to the motion, and I'm looking for dy. So I don't have t, so I'm looking for an equation that doesn't have t in it. This one's got t in it, this one's got t in it, this one here doesn't. So vf squared equals vi squared plus 2ad. Now I know that vf squared is going to be 0 because vf is 0, so I've got 0 equals vi squared plus 2ad. Now I'm looking for d, and so it's going to be vi squared minus, if I subtract it to the other side, and then I'm going to divide by 2a, is going to give me d. So if I have a go at this, vi squared is 21 squared divided by 2 times minus 9.8, and there's a negative sign there, and that gives me d. So if I grab out my calculator, and if I go if I go minus bracket 21 close bracket squared divided by 2 times minus 9.8. Either way, the minuses will cancel out, and I'll get a positive distance of 22.5. 22.5 meters equals the distance. If I use the rounded answer from the previous question, if I use the unrounded answer, I should get 23.229 meters. Either way, that answer there is worth and achieved. The Romans adjusted the catapult, so it's been adjusted, so it's not the same angle and it's not the same speed. And the next boulder hit the closest house on a hill. The boulder was launched with a velocity of 57 meters per second, which is vi squared, which is vix squared and viy squared square rooted. It hit the house when it was at its highest point. So at the highest point, it was 28 meters. So that means that dy equals 28 meters when vfy is 0 and AY is minus 9.8. So it says calculate the horizontal distance to the house, but in order to calculate the horizontal distance, I need to first calculate the time. So I'm looking for an equation that doesn't have VI in it. So I've come back over to my equations that I just had, in an equation that doesn't have VI in it. That one's got VI in it, that's got VI in it, that one's got VI in it, and that one's got VI in it. So I'm a little bit stuck. And so essentially I have to choose one. So it doesn't really matter which one I choose. And so if I get rid of all of that, and I might just choose VF squared equals VI squared plus 2AD, because I used it in the previous question. And if I work out the VI, then I can work out time. So VF squared is 0 squared equals VI squared plus 2 times minus 9.8 times the distance of 28 meters. If I grab out my calculator, 2 times minus 9.8 times 28 gives me minus 508, which equals 0 squared. And so VI actually just equals the square root of 548.8. So I grab my calculator and I square root this answer. If I square root the positive value of that answer, because it is actually positive when I move it over, I get a VI of 23.4 meters per second, which is VIY. So now I know my VIY. I can either use a triangle, and if I know that that one is VIY, which equals 23.4, and I know this is 57, I can work out that velocity there, which is helpful. So V equals 57 squared minus 23.4 squared square rooted, and so that's Vx. So Vx, if we do that again, if we go 57 squared, take away shift answer squared, and then we square root that answer, I get 51.96 meters per second. That is going really, really fast. And then I need to work out the time. So the time is in the air. So I know all these variables except for t, and so I can choose an equation that I want to. In this case, I'm going to use VF equals VI plus AT. I'm going to rearrange that for time, so I'm going to go VF minus VI, and that's going to equal AT, and then I'm going to divide by the A, so it equals T all itself. So VF, it stops at the top, minus VI. We said that VIY was 23.4, and I divide that by minus 9.8. So divide that by 9.8. I'm just ignoring the negative signs because negative to cancel. So I get 2.39 seconds. So that's how long it's in the air for. And so if we want to know the distance travelled, velocity is distance over time. So distance equals velocity x times time. Velocity x was 51.96 and the time was 2.39 seconds. So if I multiply that by 51.96, I get 124 meters. Now I think that is a pretty tough, pretty solid excellence question, which a few of you managed to get, so well done. Overall sufficiency was 7 achieves to get an achieved, 3 A's, 4 M's to get a merit, 2 A's, 2 M's and 3 E's to get excellence. Obviously this isn't marked by the new question by question marking, but still gives you an idea of what you could expect, maybe slightly longer than a typical Year 12 Mechanics question in terms of just a sheer number of questions, but pretty similar content. Hope you did well, hope you found this helpful. All God's blessings. See you later.